what if I told you there's somewhere in the world right now millions of people are clicking, tapping, and transacting at the same second? Every click, every purchase, every notification, all demanding one thing: instant response. But here's the real question: how do you handle 10 million writes per second? This is not a performance problem. Yes, but indeed, this is a physics problem. You see, traditional systems were never built for this. Databases were designed for thousands of writes, maybe tens of thousands. But at 10 million per second, locks collide, disks choke, latency explodes. Your database doesn't slow down, it collapses. At this scale, CPUs are not the bottleneck. Memory is not the bottleneck, but your coordination is. As you can see in this video, 10 million writes per second is not a linear step up, it's an exponential leap. It only happens during certain campaigns on an e-commerce platform where typically like 9 9 10 10 11 11, like even 1 1. So that is today. So standard high traffic app typically ranges from 10,000 to 50,000 TPS. But what we're seeing, a festival like 1111 Alibaba festival, this is crossed 100 million transactions per second, and as you can see, the Amazon Prime Day, the DynamoDB peaks at 146 million requests per second. This is a true testing the depths of the transactions per second. So this is called TPS. Transactions per second is called TPS, and systems catastrophically fail during these days if they are not designed for physics, and if they are not designed keeping the fundamentals of physics into consideration. So this requires a fundamental paradigm shift. So we will see deep into that. So this is where the modern system design begins. The breakthrough idea is simple. Don't write to a database, but write to a stream. Write to the future. Instead of blocking users while data is stored, you capture the intent first. You acknowledge the request. Your queues make the work, and then you process it later. But you will process it in the fraction of milliseconds. I'm not talking about 500 to 600 milliseconds, but about like 50 to 40 to 50 milliseconds. This single shift from synchronous to asynchronous changes everything. Here's how systems at the planetary scale survive. So typically, you are doing an ingested with pre-generated IDs. So that means every transaction is unique. It has a rolling global transaction number, which is unique to its own identity. And then you write these buffer into a message queue. So you are not writing to any disk, you are just writing to a memory buffer, and then tons of memory buffers, and they are being written to message queue. So once they are written to message queue, you send a response that it is request is succeeded, it's queued, but not after it is saved. So the step 4 is, so once these requests are queued, so there are consumers who actually respond to these messages in the message queue, and they act faster in storing this data. So if you see a traditional MySQL database, which is like an InnoDB specialist, so your database, the way how it writes is something like a B trees, and then a single instance in a DB just loses its general purpose, and it is not scalable for read heavy and for QPS, and then write heavy for transactions per second. So the modern one is using RocksDB. So this engine uses LSM trees, convert random IO into fast sequential disk writes. So but there is a downside to it, because you need to compact these all these records, because you are writing too much of IO, and there is a CPU contention and a IO contention when you write so much of data. So best use case is when you are doing a write intensive operation, so like on a campaign day. So typically all these stuff happens. But what we have seen now in the next generation is the hyperscale. So I'm fortunate enough I work with Alibaba X engine, which is called PolarDB X, which has sequential append, but often the compaction cost is moved to another fast storage device, which is a field programmable gateway. In short form is FPGA. So best use case is extreme write concurrency, and I also tested with the queries per second. It is quite fast compared to the normal LSM trees based something like RocksDB, where contention is high. So typically, these kind of things happens only in the transaction processing systems, like e-commerce systems as well as trading systems, and these are like high frequency writes that happens. So partition for scalability and safety. So for example, Amazon DynamoDB uses like a hard scale partitioning. So that means if it sees a partitioning or if it sees a specific partition or a shard is hard enough, then it actually uses the other partitions or shards reliability to distribute load, and it contains the failures. So there is one fundamental principle that all these internet engineering, e-commerce engineering, or even the trading systems engineering uses a certain tools called chaos engineering. Chaos engineering tools deliberately inject faults and verify this system resilience in order to understand where exactly the system could go for a toss, like, and then there's a huge white erupting exactly the way the failure happens. So chaos engineering tools are meant for actually focusing that specific space. As you can see, this is the masterclass for Alibaba's X engine and the art of offloading compaction, which we have discussed just now. So, in the regular databases which are focused on InnoDB, which is like a B tree and B plus tree, which has a random I or high page splits. I mean, there is a direct seek read performance is good enough. Even when you distribute MySQL, it is quite possible. But the problem in this case is so it is not scalable beyond certain limit. So RocksDB is quite good, and it is also have follow LSM. So, and it is a log structured and variables can multiple SSTs at a given point in time. Like, but the compaction problem is quite high in this, and because of the CPU cycles and the number of open files for the IO contention, because and it also write intensive. So if it is intensive and there is a contention among this CPU cycles or IO open files, then it is a problem again for the system. So that's where I would see Alibaba X engine has superseded all of these cases in terms of utilizing the sequential append and write amplification is optimized with very low with optimized compaction and high accelerated lookups with the FPGA introduction, and compaction overhead is offloaded to FPGA. That means there is no it's a near zero CPU. CPU utilization is quite less in terms of compaction, and it follows the extreme concurrency principle. So this is the advantage of this. So typically, all these e-commerce platforms or trading system platforms, if they are designed to be highly concurrent, they follow something called tide storage, which is like hot, warm, and cold, based upon the temperature of the partitions of the data. So this is one of the critical innovations that these that the databases should follow. And then, as I said, hyperscale heterogeneous computing. The critical innovation is offloading the compute intensive compaction logic to the third-party storage gateways like gate areas like FPGAs. This decouples storage maintenance from transaction processing. As you can see, the bottleneck is not database. Bottleneck is not is not the memory, is not the CPU, but it's the physics. The fundamental problem here is like converting random IO to sequential IO. So random IO is not scalable, as I said. So typically, that's the reason why we have to do a sequential IO and quick writes to the in-memory tables, and then solid state devices, which the tables which are on solid state devices actually will take care of actually writing the data or reading from the point seek based data. So which is quite intensive in terms of both trading systems and e-commerce based systems. So the paradigm shift from the basic problem is so instead of updating data in a single place, random IO appends all the new model is appends all writes sequentially to an in-memory buffer and flash it to disk as an immutable file. This is one of the very important things. But other problems of solving compaction and other issues are better addressed if you have an FPGA design as per Alibaba Polar DBX. So, so typically, this is a hot row conundrum when millions of writes targets a single record, right? So in a flash sale, like a viral URL's click count, thousands of requests try to update the same row. which is like there is a standard level locking that creates a lock convoy and destroys the throughput. But Alibaba's solution is like this, right? So it's called an inventor hint. So typically, what it does is it's a commit on success. So only when it has a guarantee that there is a success, it's committed. Otherwise, the lock is not removed. So it creates a dedicated lightweight FIFO queue in the memory for the hard throw. Requests are queued and processed sequentially at the RAM speed, but the it is not blocked. That's one of the key things that you can see here. So a single row can sustain up to 31,000 updates per second. So I'll give you an example why this is the scenario, right? So let's say in a fast e-commerce platform where you are using APIs to trigger uh, orders, buy and sell, like order, add to cart, buy and sell. Sometimes it's like discard from the cart, discard from. So there are like continuous set of updates that happens on an, for example, not so many updates on an e-commerce platform. Probably you can say 100 updates per second, but not on a trading system. Trading system is meant to an algorithmic trading system is meant to handle those many number of updates per second. So in those cases, like let's say not 31,000 updates per second, but at least like 100 to 500 updates per second. We're talking about updates. That means there's a row locking in a traditional database. So how are you going to handle this specific part? So which is only by the inventor hint. As you can see from this picture, so lightweight FIFO queue in memory bypasses heavyweight row locks and processed at RAM speed, and it's a hot row. It's a hot row. So this is one of the key applications for the URL shortener, and then thousands of updates on a single row. So which is very crucial to understand. So when a single node is no longer enough, it's the imperative of the dynamic sharding. So you need to actually spread your data across multiple machines when single machine is not a choice, right? So what happens is, so that's where the sharding comes into principle. So the typically the functionality of sharding goes like this. So you will be choosing certain so the basic approach is a partition will be there, and the partition can have multiple shards. So that means there is a partition key and as well as a shard key. So you can choose to have multiple keys like this, and then the you can use a sequential ID, but it will be catastrophic, right? So all writes hit a single partition, but you need to have a shard key that can be spread across multiple disks. So the partition key determines, okay, let's say it is today's date, but the shard key determines, okay, how many places that I can spread this into. So that's why you always need a dynamic sharding, but also shards need rebalancing, saying that, okay, for example, if you have not employed a proper shard key, your data will be it will not be balanced uniformly, and it is like, let's say you have 20 shards or 30 shards. If you don't have a balanced shard key, your data will stay only in 5 to 6 shards rather than compared to all the different shards that you're having right now. So, Amazon DynamoDB and how it self heals with the adaptive capacity. As I said, DynamoDB is quite huge, and we are saying about 145 million transactions per second. So, that means how business gets done in Amazon, right? So, hard partition detected. So, what happens when a hard partition detected? So, that means it is nearing the threshold. That means the throughput has been needs to be boosted. So what it does, so then it says what is hot. So that means there is a lot of traffic in it. That means the systems are getting uh, heat too much of the wide traffic that you are seeing in there. So that systems are actually becoming hot. So that indirectly transits into like whether the heat is persisted or not. If a heat is persistent, yes, okay, then it splits the partitions into two. The throughput doubles. So because that again, it segments the partition into the multiple parts, so that it actually borrows the capacity, and it splits the partition into two. So which is one of the fundamental things of dynamic partitioning, and of course it happens across many machines. That means sharding is also taken care. So this by example, like how many 145 million transactions per second, and how the adaptive capacity is solution is being used here by splitting it into transparent internal splits, dividing the hot partition into new ones, where exactly doubles the capacity of the same thing, but at the same time not getting the systems burnt, and at the same time dividing the heat and reducing the reducing the bottleneck of failure on. So it's fundamentally these systems are, you don't design them for failures. Actually, you anticipate the failures, and then your systems are being resilient for those things because of your chaos engineering principles, and then have to they will have to regain to the original shape. That's how these systems are designed, with the self healing and with adaptive capacity. The next thing is about Shopify. So this is again a masterclass. So Shopify pods. So how Shopify, if you don't know about Shopify is a plethora of e-commerce systems that it is holding across the world, and particularly so much in North America, and then Europe, and also in Asia and Australia. So that's the Shopify's pods, and it containing the blast radius. What does that mean? So Shopify pods limit themselves to an application. So they have a blast radius of the application containment. So containment, and then any failures are under that specific jurisdiction of that specific pod. So if you want to have because Shopify is a fundamental principle is all about shops, and then they accelerate them, and then they scale them. So that's how. So your account or your pod will not impact any other shop's pod if it goes for a toss. So that's the main thing. So any noisy merchant crashes on a pod, only the shops of that pod are affected. Other 99% of the platform remains operational. So this is one of the main interesting principles that is being used, which is called bulk heading principle. Instead of sharding just the database, Shopify shards the entire application stack. So that means none of the application has. So this is like a micro containment of that specific shop, and then the pods are automatically scaled based upon it. So even though there is a failure, the shop pods itself gets failed because they didn't employ proper application scaling steps in the Shopify. That's the key difference here. So this is one of the also containing the blast radius is also one of the methodologies that you can see how you can scale in these system engineering. Yes. So the final thing is about how we talked about all the bits and pieces of things, how we have to encapsulate, how we have to scale up, how we have to do the things, but the real nervous system is how the signals flow from one pod to another pod, client to API, write request to message queues to consumers to actually writing to the memory buffers to the actual disk. So this is the entire structure that has to be handled, and there are different things like, yes, speed provides back pressure, and then the entire system from crashing. So, for example, if you think about the messaging open source messaging software, which is called Kafka at least once, exactly once semantics. Both are there. At least once in the previous days of Kafka, exactly once now. But yeah, so you can't put a massive scale of Kafka in between these things. Some of them can scale, some of them may not. So that's the reason why you need to have a proper asynchronous mandate. That means the system must decouple the intent to write from the execution of the write. So the message queue acts as a massive durable buffer. So it ingests writes at an extreme speed and provides back pressure, preventing the entire system from crashing. That means if the consumer is not up to the mark in order to actually provide the data, it should provide a durable setting for the queue. That means a persistent mechanism of even retrieving the messages, even if the consumers are lagging in with the with the offset of the total data that is present in a queue. So that's why it's called a shock absorber. So the nervous system has to be stable in any system engineering problem. What? Okay. We thought Kafka was a holy grail, and now Kafka is is a limitation. So that means what's happening here. So tens of thousands of topics, the broker must manage thousands of open file handles. That's true. So even though the Kafka nodes are spread across, then there are multiple nodes that are being created, which has a random disk I/O, performance degradations, open files problems, and then increment of logs because some fellow switched on a debug log on a specific Kafka worker. Okay, so these are the problems that you see. But what Alibaba came up with, it's called RocketMQ. RocketMQ is a unified commit log architecture. So now, as I said, this RocketMQ is being practiced by many e-commerce systems as well as trading systems, because these messages are all sequentially write to a single massive log file metadata. So if I might say, Raft is one of the best parts of to it. So they then dispatch asynchronously to lightweight consume queues. And then RocketMQ allows this separation to support thousands of topics without a drop in the write throughput. That means there is a read topic, then there is a write topic. So the topics are quite different, and they are done at the speed of less than a millisecond. So that's the advantage that you see of RocketMQs. And then it's a superior for business critical parts where latency and transaction integrity are key. Kafka still remains a standard for observability parts where you have clickstream analytics, say for example like log, clickstream log, audit log, all these log strands, like a ELK stack for that case, and then like for archival purposes of writing the data back into Kafka, and then or for reading the data like in a streaming way where latencies are not a problem, and then the data has to be ingested into the data lake. Kafka is still a go to one, and but RabbitMQ seriously it needs to be there when it is a transaction critical systems, and then the when and the communication is paramount between these systems. So you need to go for something like a RocketMQ, which is like way better in terms of like how the production queues and consumption queues, and then how the dispatch is, and how the dead letter queues are maintained, all of that at a distributed scale. So if you have heard about something like RabbitMQ, so to me it's more of a RabbitMQ on steroids with the distributed processing. So that's where RocketMQ comes into picture. So, as you know, acid is atomicity, consistency, isolation, and yeah. So, maintaining acid consistency across thousands of nodes is impossible, sacrificing availability. But the industry has moved to the base model, basically available, soft state, eventual consistency. So this is there are two patterns that emerge out of this process. One is the saga pattern. A saga is a sequence of a local transaction. Each step updates a local to publish an event to trigger to the next step. If a step fails, they execute a series of compensating transactions to undo the changes made by previous steps. So one of the key things. So, but Alibaba's Sierra framework, it provides a state machine to orchestrate these sagas asynchronously. No database locks are held across the network, enabling high throughput. So what does that mean? So that means you have a series of inserts, updates, deletes, and rewrites, many updates. So this entire thing is called a saga. Okay. So, and for some reason this entire saga is wrong. You need to go to a checkpoint that is in the previous state. So what you have to do is to roll back an entire saga, which is there by Alibaba's Sierra framework. So that's what it provides. It's a it's a rolling state machine of states. What does it mean? It's like you have a union of certain number of states from point time 1 to time 2, and then time 2 to time 3. You somehow realize that time 1 to time 2 is entirely wrong, so you have to roll back from time 3 to time 2, time 2 to time 1, because T1 to T2 is completely wrong. So that means you have to migrate to T0. T0 is the actual one. So this Sierra framework helps you in in orchestrating these sagas and then roll backing these sagas when problems are happening. So that's what this is about. Fantastic. Resilience engineering. Failure is not an option, it's a certainty. Yes, that's true. So when you see large amount of transactions like these, systems are behave to scale, but for some chance, some of the nodes go down. And if you are a new player in the e-commerce and you haven't done it, international chaos injections, chaos problems, or let's say there is a degradation among some payment gateways. So how do you handle it? So you should be able to send notifications and notifications to those people to use a different payment systems, or Later you can say, okay, cache mode or a different ways. So these are the ways how you can think of in terms of payment failures or order failures, a lot of things. But your system has to have a genetic DNA of having chaos inside the systems engineering. So typically, your software failures are not probabilities; they are constants. The system must be designed to withstand all these and even benefit from them of how you do it. So some of the tools of the trade: Chaos Blade, built by Alibaba. So JVM OOM errors and RPC delays all are fine-grained fault injections. And Gremlin is one of the another companies that it has safe chaos experiments on a subset of traffic. Fortunately, I've been part of both e-commerce and trading systems to actually navigate this one. So the blueprint, as I said, ingress and ID generation. I won't go deep into that. This has covered everything. Asynchronous write buffering. So you have rocket time queue to handle all these buffers and then happily go to from publish to subscribe queues and then navigate to the final state. Tied storage and sharding, Polity with X engine, which supports FPGAs, fantastic. Alice equals inventory hint or adaptive capacity like Amazon. Multi-level caching. So yeah, as I said, so there is one other company which is called JD Sports, I think. So which uses something like JMDBQ or Redis. So you can actually use a Bloom filter, even prevents requests for invalid short IDs from ever hitting the storage layer. So that's one of the level caching and safety. Resilience, Shopify style pods, Chaos Blade. If you want to do fault injections into your entire system, think of this like an entire semiconductor circuit where you can inject faults and find out like where exactly what happens to one port. If you give a fault to one port, what happens to the other port? So it's a similar approach. So chaos monkey used from Netflix side. So now it's a chaos engineering has been built out of it. So what happens is chaos blade. It's typically cuts through every system's thing and then experiments it and ensure graceful degradation if any system is down. So that's how the resilience is built on the latest systems. So this is the spec sheet. Layer technology choice, Nginx plus DPDK, regeneration service. So it's something like KGS. Buffer is a RocketMQ. Cache, JMDB, Redis cluster. Storage. If you see PolarDB X engine is fine, but you also see AWS Aurora has fantastic things, and Google's DynamoDB and Azure's similar cloud, similar columnar databases. And sharding, it's a consistent hashing, so even distribution, dynamic notation, ensure the shardings are balanced. This is one of the important things. And safety and chaos engineering has to be built into the systems engineering. So that's one of the main important things that I'm saying. So this entire thing is focusing only on how you deal with the data, how you deal with the TPS and QPS and transactions and everything. So this gives us this is not a complete overview, but it just gives a core philosophical shift on how you're writing to your database and when do you have to shift from 1 million transactions per second to 10 million transactions. So when you hit 1 million transactions per second, you should have already been developed a 10 million transactions per second kind of a system. So typically that's how it'll work. So how you are at 100K and how you are at 1 million, how you are at 10 million, how you are at. So it depends upon how you progressively transform yourself. But instead, if you can build it upfront, but by actually containing the costs and see how it goes, because the paradigm shift or even the shift from 1 million to 2 million, 100K to 1 million, it can be overnight. So you don't even know. So that's why I was introducing this one of the interesting research that I've done and I put through with my thinking and approach. So thank you. So this is the blueprint of modern system architecture. We have also one more infographic in the beginning. So LSM trees, monolithics to microservices, containing through blast radius, adaptive scalability, and then using offloading a compaction space to compaction load to another one, and QPS to again through FPGA high throughput, high QPS reads, and then introducing chaos engineering and figuring out where exactly system goes down. So these are the fundamental things that you are actually need to follow. Thank you. So this is one of the things through Deep Tech X. So thank you for listening to our series. Enjoy.